Imagine for a moment that you are looking at a perfectly round ball sitting on top of a hill. The ball is balanced, motionless, in complete harmony with its surroundings. In this position, the ball has no preferred direction. It could roll left, it could roll right, it could roll forward or backward. All possibilities are equal. This is a state of symmetry, a fragile, delicate balance where every direction looks the same. Now, picture what happens next. The ball wobbles ever so slightly, and suddenly it rolls down the hill. But it doesn't roll in every direction at once. It picks just one. Maybe left, maybe right. That choice breaks the perfect balance. The symmetry is gone. And from that one choice, a completely new reality emerges. This simple image captures the essence of one of the deepest and most mysterious principles in physics: symmetry breaking at the quantum level. It sounds abstract, but it is the very reason why our universe has structure. Without it, there would be no galaxies, no stars, no atoms, and no you watching this right now. At its core, physics is obsessed with symmetry. Symmetry is not just about beauty, it's about order and rules. If you spin a perfect sphere, it looks the same from every angle. That's rotational symmetry. If you reflect a snowflake in a mirror, it looks nearly identical. That's mirror symmetry. Symmetry tells us that nature follows certain patterns, and these patterns are so deep that they dictate the fundamental laws of the universe. In fact, some of the most powerful discoveries in physics came from studying symmetry. For example, Noether's theorem, one of the most profound ideas in all science, tells us that every symmetry in nature corresponds to a conservation law. The symmetry of space gives us conservation of momentum. The symmetry of time gives us conservation of energy. Symmetry is the skeleton of reality. But here's the paradox. If the universe loves symmetry so much, why is it broken? Why do we live in a world that looks messy and uneven? Why do galaxies cluster in some places and leave vast voids in others? Why does matter exist at all, instead of being perfectly canceled out by antimatter? The answer lies in spontaneous symmetry breaking, a phenomenon that hides behind the curtain of quantum physics. Let's rewind the clock to the earliest moments of the universe. Right after the Big Bang, the universe was unimaginably hot and dense. In that inferno, forces as we know them today, gravity, electromagnetism, the strong and weak nuclear forces, did not exist separately. They were united, blended into a single, elegant force. The universe at that time was like the ball on top of the hill, perfectly symmetrical. No direction was different from any other. But as the universe expanded and cooled, that perfect balance could not hold. Like the ball rolling off the hill, the universe chose a direction. The forces began to separate. Gravity peeled away first. Later, the strong nuclear force separated from the electro-weak force. And finally, the weak and electromagnetic forces split, thanks to a deep act of symmetry breaking. From one elegant unity came the four distinct forces of nature. This breaking of symmetry wasn't a mistake. It was creation itself. The structure of everything we know, from stars to quarks, was born out of this act of cosmic imbalance. Here's where it gets even stranger. Symmetry breaking doesn't just explain why forces split. It explains why particles have mass. Think about that for a second. Mass, the very thing that makes you solid, that lets Earth hold you with gravity, that allows stars to burn, exists because of broken symmetry. In the standard model of particle physics, there is a field that permeates all of space, the Higgs field. Imagine it like a cosmic molasses spread everywhere in the universe. In the early universe, this field was perfectly symmetrical, with no preference, like a glassy calm ocean. But then symmetry broke. The Higgs field shifted, choosing a particular value. And when that happened, particles moving through this field began to resist, as if trudging through invisible syrup. That resistance is what we call mass. Without the Higgs mechanism, every particle would zip around at the speed of light, weightless and intangible. Atoms would never form. Chemistry would never exist. Life would be impossible. In other words, the reason you have weight when you step on a scale, the reason you don't float off into the void, is because symmetry at the quantum level decided to break. But symmetry breaking goes even deeper than physics textbooks suggest. In many ways, it is a story of how order arises out of chaos. Consider superconductivity. In ordinary materials, electrons scatter randomly, wasting energy as heat. But when certain materials are cooled close to absolute zero, something magical happens. The electrons spontaneously pair up in a perfectly coordinated way. The symmetry of randomness is broken, replaced by an ordered state. Suddenly, electricity flows forever without resistance. This is quantum symmetry breaking in action, showing us new phases of matter that defy intuition. Another stunning example is the early distribution of matter and antimatter. According to symmetry, the Big Bang should have produced equal amounts of both. They should have annihilated each other instantly, leaving nothing but light. Yet here we are, living in a universe made of matter. Why? Because somehow symmetry tilted just slightly in favor of matter. A tiny asymmetry, perhaps 1 part in a billion, was enough to tip the cosmic scales. That imbalance is the reason you exist to even ask the question. If we step back, symmetry breaking seems less like a flaw and more like a creative act. It is the universe making a choice. The ball at the top of the hill doesn't stay in perfect balance forever. It must roll, and in rolling, it writes the history of everything. What's truly jaw-dropping is how symmetry breaking may connect to the deepest mysteries we haven't solved yet. Could dark matter, the invisible substance holding galaxies together, be a product of a broken symmetry we haven't discovered? Could dark energy, the force accelerating the universe's expansion, be the shadow of another symmetry shift at the quantum level? Some physicists suspect entire hidden worlds, mirror universes of particles, might exist because of symmetries that broke differently from ours. And then there is the ultimate question. Why is there something rather than nothing? If perfect symmetry ruled absolutely, perhaps nothingness would have been the only option. But the cracks in symmetry gave rise to imperfection, and that imperfection gave rise to stars, planets, and consciousness itself. So next time you see a snowflake, notice its near-perfect six-fold symmetry, but also the tiny irregularities that make it unique. Remember that the beauty of our universe lies not in flawless balance, but in broken harmony. Symmetry at the quantum level was shattered, and from those cracks, reality was born. We like to think of broken things as failures. But in the universe, broken symmetry is creation. It is the breath that made existence possible. It is the reason the void became full, the reason light dances with matter, the reason you are here, watching, thinking, and wondering. And maybe, just maybe, the greatest secret of the cosmos is this: perfection is sterile. Only by breaking symmetry does the universe learn how to sing. That is the story of symmetry breaking at the quantum level. A story where the fall of balance became the rise of reality.